So my talk will be about the mathematical, and before I go to the mathematics, so I want to show one of the applications about the things I'm going to talk later. So this is one of the project which was we were working. This was proposed by the Christian Michelsen Research Center in Bergen, and we proposed this project to the Norwegian Public Road Administration Authority. So essentially, we are trying to utilize, you have the traffic cameras all over the country. We want to do automatic information extraction from those cameras. So the first thing we did is that here is a list of all the cameras in Norway, so which along the way or in the center. And the first thing we did is that we develop, this is the Christian Michelsen Research, develop a web service. So we have the computation is running in the company, but the photo you can take from through the web page from anywhere. So you can see that this is real-time imaging, and this is just a few minutes ago. And then this is one of the cameras. And what we did, you see, we developed a method to detect the road condition. So essentially, we try to classify the road into 5 categories. So one is dry, another is white, and third one is icy, and fourth one is snowy, and the last one is there's both snow and icy. So it's essentially automatically determine the road condition, and then you can send a message, you see, to the road authorities. You see, they need to send a vehicle to clean the road. It's too icy. You need to send a vehicle to put some liquid or salt on the road during the winter. You see that this is for one of the cameras. You can see that we detect here is wet, and you can pick any other camera. All those images are real time. So you just choose the camera, you click, you see that it's real time just a few minutes ago, and here's the road. We detect, you see that this is also wet. And then I can show you some of the camera maybe which is in the northern part of Norway. So probably you move very to here. If I click, you see that this will be dry. This is also wet. So it's a dry, but we classify as wet. You can see that there is a snow. And there are even some cameras in the very northern part of Norway. Even now, there's a lot of snow there, so we automatic. So this is the first application we were doing with the Norwegian you see, public road authorities. But we are hoping, you see, that we can do more in this direction to automatically extract information from all those cameras. So those cameras are standing there all the time. And there are a lot of information you can extract. So it's not only you say I click on the web page, I see, it's running in my home, near my home, right? And so this is a project we have been running, and my talk is more related to some of the methods, you see, research things we have been doing. It's somehow related to this project. And so I'm going to talk about use some of the things on graphs. How do you get a global minimizer related to graphs, and then how do you do the classification as what I was showing later. This is joint work with Andrea Bertozzi, professor from UCLA, Egilbae, who was my PhD student and a postdoc in UCLA, and she's a PhD student in UCLA. And the industry project I was showing, which is that one, we are just on with the first phase now, so which will continue. We hope, you see, we could do more automatic information extraction. And Jin-Young Yu from SEMA, Christian Michelsen Research Center, he's a project leader. I'm a senior scientific consultant for the company. So we discuss about the methods, you see what are the methods we can use. So so today I'm going to talk mostly about 3 things. So this is something which has been developed earlier in the literature, or some by our group for image segmentation or classification. And those are things mostly I want to talk. It's about how do you use those methods to classify or classify high-dimensional data. And then later also I'll quickly mention, you see, how do you use those things for Checkercut. We know that there are many problems which can be, say, the interface or classification problems. There are a lot of models, right? And then you can use a lot of methods. You see active control, level set, phase field. But you see that most of those problems When you solve them, you come to a nonlinear and non-convex problem, and then you get slow convergence, you get stuck with local minimizers. But however, you see that this problem can be over. You see, you can get rid of it if you use the proper things, especially if we use those kind of graph-related methods. So essentially, you see that here is a graph, and then you can solve a mean cut Marx flow on this graph, and then you see the mean cut is equivalent to the Marx flow, and then how do we use this one? You see, for classification of data, you see that if you have a two-dimensional data, if you want to classify this data into two classes, what you do is you construct such a kind of virtual graph. You see every point, you connect S to every point to T, and then you have natural connections. And then you see that you can assign proper capacity on this graph, and then you do a mean cut or do Marx flow, and that will give a classification. And especially for this graph, if we assume you see the capacity here is F1, capacity here is F2, between the points, you have a capacity which is a GPQ, and those are capacity. And then you see that if you cut, this cut is you cut the edges here, cut the edge here, cut this one, so this will produce a cut. And we want to find a cut which is minimum cost. And then you see that if you have F1, F2, so you see that if the nodes is associated with 1, and this will be labeled as 0, associated with 1. If this node is, if the cut, after the cut, if this point is connected to T, we see this is labeled 0. In this way, you see that the cost of the cut is essentially, you see those edges are cutted, those edges are cutted, and those edges. So you have three parts. So you see, you sum the F1 things, F2s, and so therefore a mean cut, you can just write in such a way. So this is the mean cut over such a graph. And then you see that we are going to make it continuous. So therefore, you see, we don't, so we think that this mean cut is a discretization of a continuous problem. So we say continuous mean cut or continuous Marx flow. So that means you have a region, every point S is connected to every point connected to T. And then you see that mean cut in the continuous case is exactly this way. So the last two terms is so-called anisotrophic TV, which measures the length of the cut. Plus you see G1, G2 as a weight. And then you see that this is a continuous version. You see that in the discretized case, we know that the mean cut is equivalent to the Marx flow. You see the discretized case, you can write the Marx flow in such a form. So you see that the flow coming from here and go to T, and there's a conservation of flow. So therefore, if you sum all the flow here, that equals the total amount of the flow. But then you have the constraints of the flow between the pixels, and you have a flow of the flow here, and this is conservation. And this is a discretized formulation of the Marx flow. And this also you can make it continuous. So therefore, the continuous counterpart of the Marx flow will be such a thing. You see every point connected, and then you integrate all the flow here, and those are the, you see, flow constraints in x, y directions. These are flow conservation. So therefore, this is a continuous Marx flow of that system. So in the discretized case, we know that the mean cut is equivalent to the continuous to the Marx flow. But in the continuous case, are they equivalent or not? And so we can easily show. And also you see that in the discretized case, mostly you can only handle flow constraint in this form, but in the continuous case, we can handle even another form. You see that those two different forms, when you do the mean cut Marx flow, it produces a different measurement of the length of the cut. This will give you, if you discretize it, this will the length of the cut will be measured in the Manhattan distance. If you do this one, you will measure the cut of the length in the Euclidean distance. But the continuous continuous method we are going to show handles both cases. But the traditional graph cut, mostly you can only handle such a thing, or you need to increase the number of neighbors. And so the next thing I'm going to show that you have such a continuous Marx flow. This is Marx flow in such a system. And we're going to show that it's equivalent to the mean cut. So how do you do it? So essentially, you see that you maximize the thing under those constraints with such a kind of flow conservation. And then if you use Lagrangian to deal with this flow conservation, you maximize the flow, you minimize the Lagrangian here, you put it in Lagrangian. And then you see that you have a PS. If you move this divergence by integration by part, you get gradient U. And then it becomes all linear with the PS, Q, PT, all linear. All linear, and you also have this kind of upper bound constraint. So you can easily do a min-max switch. And then you see, because they're linear, you minimize those constraints. It's easy. You can easily eliminate all the flow variables. It become become minimization for the Lagrangian. And this is essentially the Lagrangian of the flow conservation. You must satisfy this one. And then you can see that this is differ from a min cut. It's only the difference is here, 0, 1. So original min cut must equal to 0 or 1. But here the Lagrangian must be between 0 and 1. And this is the only difference. So in this way, you see that, in fact, this model has been proposed in this paper a long time ago and to solve this kind of so-called the transversal model. So in this way, we are showing that so we have, you see, we started from a discretized graph and we come to a continuous thing. In the continuous case, you see, we are talking about three problems. So this is the min cut problem, and this is Lagrangian. So essentially the due of the Mach flow, this is the Mach flow problem. So those three problems, in fact, they are completely equivalent. So if you solve one of them, and then you solve the other two, and then you see that once you get the solution for any of them, you get a classification of the data into two classes, 0, 1 into two classes. You see that traditionally, mostly you use other method to solve the min cut Mach flow over the graph. So here you see that due to this kind of primal due, so we use you see traditional method is like Lagrangian. So here so here we use lambda instead of u as Lagrangian, and we also add the penalization. You see that here we alternatively maximize the flow. Here we do a gradient descent for the cut. Lambda will be the cut. At convergence will be cut. In this way, you see that this is a different algorithm to find the min cut or Mach flow over a graph. And especially you see that this one is a quadratic over each node. This is quadratic each node, so it's very easy to compute. And this is somehow, you see, you need to solve some gradient. Q, there is a gradient, and then mostly we use a few steps of gradient descent with a projection. So therefore, totally the algorithm is very cheap to compute per iteration. And most we observe that if you use this one for classification, mostly you don't need so many iterations. You use 100, around 100, sometimes few hundred. So which is really much faster. And moreover, you see that we have two versions. Both versions you can work both easily. So you see, if you use a traditional graph cut, you're not minimizing the area. You're minimize, you see, the Manhattan distance. So this is if you do a motion by mean curvature. So this is the ball you produce. If you use the new method, you see we can really produce a ball due to the Euclidean distance or area you measure. And moreover, you see that the new algorithm is fully parallel. You can easily implement on GPU, and the cost per iteration is just linear. You see that you have 4 steps. It's linear to the number of nodes, and to this radius there is no difference. But however, you see that here is a notation. It's different from NP hard. You see this problem is NP hard, so therefore there is no polynomial time solution. But however, here we are talking about per iteration, and mostly numerical. We observe that you don't need many iterations for that algorithm. And so therefore, using that approach, you can classify data into 2 classes. If you want to classify into many classes, multi-phases, how do you do? So essentially, you can use about 3 different ways. And the first way, you see that instead of solving one binary function, you introduce n binary function. If you want to classify into n classes, normally we assume n is known. And so therefore, you see that this the phi 1 equal to 1 in region 1, otherwise 0, phi 2 equal to 1 in region 2 are 0, phi 3. So those are the phi I are the characteristic functions. And then you see that once you get the characteristic functions, and then you get the corresponding regions. Each characteristic function must be 0, 1. There some must be 1, so only one of them can be 1. The other must be 0. So in this way, you see that you can really extend the earlier approach from a 2-phase into arbitrary multi-phases. What we do, you see that what we do is so when I finish the 3 approaches, I will come back. Well, you see what's the thing we do, and we also want to mention in the literature there is a number of other approaches, which is you see there are some differences. And the second approach is that instead of using n-characteristic functions, you can use a vector function. So each function can be between 0 and 1. So if you use the d functions, and then you can get 2d phases. So here you see that if d equal to 1, the two ends is 2 phase. D equal to, you get 4. Here this is 8. So if you use a d function, you can classify 2d phases. And more generally, you see that if each of the ui, you take b labels, and you can take so many functions. Also, you see that this idea originally, you see that in the Vesey-Chang paper, and also in the, I think in their group, they have a very good way. But you see, what we are doing, you see that also when I finish the last approach, I will say what's the things we have been doing. So the last approach is that instead of using the first one use n function, the other one use you see 2d, you can get the 2d phases, and this one you see you just use one function to represent the n phases. So each phase you have one label. So you see like equal to 1, the phase 1, equal to 2, phase 2, equal to 3. So in this case, you see that you just use one label, and you can construct you see n phases. You see that there is a number of approaches in the literature, and this idea, I think I think he came up with this idea much earlier. It can be interpreted in this way, and this is a very popular paper published in Science Imaging. You see that we are proposing you use 3 approaches to solve the multi-phase classification. Each of those ones, we in fact turn it into a 2-phase problem in the end. So we always turn all those 3 approaches in the end to the 2-phase problem. We construct, you see, there is a mean cut, there is a marked flow, there is a continuous mean cut, continuous marked flow, and we also have the discretized graph. So for all those 3 approaches. And then you see that you can use any of those approaches for classify a data into multi-classes. However, the cost increases as this n increases. So it's a linear increasing with a phase number. So in some cases, you see that if you really need to use many phases, or you don't know where is the true number of phases, you use a huge number of phases, and in the end, many of them become empty, and then you pay a cost if you use a larger number of phases. And then we have been using this one for image segmentation, or you can use it for stereo reconstruction or something. And the reason thing we did is to use it to classify high dimensional data, and this is also used in the root condition you see detection. So essentially, you see that you have some very high dimensional data. You know that how many classes you want to classify the data into. You see like a handwriting. You know that there's 10 classes in the data, right? So the n is given. N is given. So we still, you see, use the traditional approach. You see, each data is regarded vertex in a graph, and then there is a connection between all the vertices. And then you see, assuming there is already exists a distance between the x is one of the data, y is another. Assume there is already a measurement of this distance, and then we can construct the capacity between between the points on the edges. You define capacity either in this way. So those are some kind of popular choices in the literature. And then was just as in the previous talk, you see that once you come to the graph, you see how do you order the graph may become a problem. So essentially what we use, you see, we use a non-local notation. So which means that this one will overcome, you see, how do you order the graphs? Because you see that every point is connected to every other point in the graph, and you define the non-local derivative in such a way. And then you see if you define, this is the so-called non-local gradient. After you define non-local gradient, you easily get the divergence corresponding to the non-local gradient, and then they satisfy this natural deal. In this way, you see that how do you order the graph really doesn't matter. Really doesn't matter. You see that once you do that one, and here is we use this very simple model to classify the graph into 2 classes. So the graph is you have so many vertices. You classify into V. You classify in, or here is a table. Here is the S, and the complement of S. And then you see that when you try to find this S, So the cost, so Wxy is the cost between the, this should be minimized. This should be minimized. So this is a simplistic model to classify the data into two classes. If you want to classify into more classes, you just use the several extensions we talked about in the beginning. And then you see that it can be, once we have introduced this total variation of lambda, so which was essentially, you see that this is the non-local total variation of lambda, and then you can write was exactly this model. You can write in such a way: lambda between 0 and 1, and this is the total variation of lambda with a weighting function. Here we are adding a fidelity term. The fidelity term is essentially the lambda 0. So we assume you see lambda 0, some points are pre-classified. So you are either class 1 or class 2. This eta equal to 1 in the classified points equal to 0. So, so you see that this will trying to penalize the lambda you obtain should be close to the, or should be close or equal to the pre-classified points. And in this way that you put this term as a fidelity term here, and this one measures the length between the classes, and so therefore this classification model easily becomes such a thing. And once we come to here, you can see that this is something very similar to what we have been talking earlier. And so you see that by defining some functions, you introduce those functions, and then we can prove. You see that you do a little modification of the fidelity term, and we can prove this is the same thing as written here. We can prove. You see that this is equivalent to this one, equivalent to this one. So which means that if you get a global minimizer for this problem, if you threshold for any value between 0 and 1, it is a global minimizer of this problem. And on the other hand, if you get global minimizer of this one, it's also global minimizer of that problem. So you can prove that those two problems are equivalent if you solve one of the. Moreover, from the discussions we were talking earlier, this will be the due of a Mach floor, and this was the mean cut. This was the mean cut. And for the algorithm, we're still using you see the very similar algorithm. We just extend it to this new graph. You maximize the floor, and you do gradient descent for the Lagrangian, and this will become a cut. However, and the algorithm which we have been using for image segmentation, here we use it for machine learning. However, there is one essential difference. So here you can see the divergence. Here you can see the divergence. You see, for image segmentation, once you calculate this divergence, you just need to calculate the difference with your neighbors. Normally, it's 4 neighbors. But on a graph, you see every point is connected to every point. So if I want 1 million graph, you see this divergence costs you 1 million times 1 million. And that really is very, very costly. So you cannot pay that much. So what we did is essentially see that in the calculation, we replace this divergence by the nearest neighbors. Mostly we pick about 5 nearest neighbors or 10 nearest neighbors, depending on the application. So you only calculate the divergence with the nearest neighbors. All the other divergence is said to be 0. So this is one of the approaches to overcome this problem. There's another way that you calculate, as Professor Edwin, so you calculate the spectral, but you don't calculate the whole spectral, you just calculate the first few, use that one to compute the divergence or gradient. And this is what we use, and then it's, the efficiency of this one is not very high compared with the image segmentation. We have been, how much time do you have?
Well, if we want questions, about 2 minutes.
Oh, okay. Then I need to do very quick. So we have been testing on this algorithm on this handwriting data. Also, we tested on the bank. Those are the standard benchmark testing. We tested on the 2 more one. And so here is essentially you see with different configurations. So here is how many points are pre-classified. Here you see that you see when you start the algorithm, you can start randomly. And the fidelity points, you can also choose randomly or choose, you see, over the corner points. Here you see that both are random. Here the initialization, you start with good initialization. Here is random, but the pre-classified points you choose over the corner, and this is similar. The banknote you see completely random 2 mode. And here is the accuracy. So here is how many points are pre-classified. Here is the accuracy. And the max flow, you see that really, for especially here, you see that the other methods become much lower, but the max flow and this Lagrangian, we still see very high accuracy. Here you see that it's always for those test cases, you see that the new method is always produce very high accuracy. Here is visualize the MNIST data. And here you see that the yellow points and the pink points are the points with the yellow or maybe the green are the predetermined. The pink points were initial value. Here the yellow and green, so here is the start with. And then you see that both methods produce quite good. But here is the difficult situation that we choose the pre-classified points just over the corner here, and then the convex method still works, but the non-convex method fails. And here is also, you see that even you start with a good, this is a good initialization, also still you cannot make this to work. Cannot make this to work. So in the easy case, you see that the different methods works, but the difficult case is the convex relaxation always works, and global minimization all works, but not the other method. So here is I think is in terms of timing, you can see here is the number of iteration. Mostly we take a few hundred iteration, but this one take much more. And the timing is just a number of seconds. And then, however, we notice that this is one method we call MBO. This always take very little iterations, and then the time is very fast. But mostly accuracy for this one, for the difficult cases, are much poorer than the global minimization methods. Especially, it's very impressive if you look at the image, because we are minimize the image, and then try to see that which method produce the best image. So here is a different cases. Here is the initial image. Here is the final image. You can see that the Mach flow always produce smallest, but in those two cases, you see other method for much higher image. Some of the cases produce very similar, but it's always you see always the Mach flow always produce the smallest image, and then yeah. So this is more impressive than only look at the result. And so therefore, also to extend the methods to a little more general cases, instead of just minimize the cut cost, we have been also trying to minimize like a Chicker ratio. So essentially here is the cost of a cut. You also is divided by the area. So you minimize the cost and maximize the area. And for the Chicker ratio, we can also use these kind of approaches to transfer into a binary minimization problem. We can prove that those two are equivalent. So here is a median, and then later we can again prove. You see that if you denote lambda as a Chicker ratio, you do some kind of min-max. At least when lambda is fixing, how do you classify this U? We can use the global minimization method to do it and still produce better result. And this is again, you see that you take into the area effect into the model, and global optimization for U is possible for fixed lambda. And then also you see the Chicker ratio you can also extend to multiphase. Instead of two classes, you can. So this is one of the model we use. Again, you see that once lambda is fixed, and this problem is one of the approach we talked earlier. We can easily also use the method to get this one. We haven't done a lot of. This is one of the 4 classes we can do this one. I think yeah. So in the beginning, you have been showing is we use. So when we do the condition detection, so what we did, you see, we each pixel we get a feature vector around 80, and from that feature vector we classify into 5 classes, and with the predetermined classes, and that we got about accuracy about 85% or something. So we hope we can still get better, and there's something more. Here are some of the references from our group. I think earlier I'm pointing to some other groups, but here is related publication, what we have done to the things I've been talking. Thank you.
I think we've got time for probably 2 or 3 questions. So, has anybody got any questions? Well, I'd like to sort of say, I've just got back from Mallorca cycling, and thank God I'm not in Norway. It's cold enough here. Are there any questions? Yeah, Bob.
In terms of the road surveillance, suppose there's fog or haze, you can't see the surface of the road.
Oh yeah, so those cameras are always are fixed cameras. So it's mounted all over the country, and that leads to very, very long. See, all the cameras are pointing to the road. You can, but maybe sometime when there are too many cars, you cannot see the road. And
Actually, what I was talking about maybe is fog or haze.
In those cases, maybe the accuracy is much lower. But still, you see that the images we really classify, we say 85% of accuracy, and those are very poor condition. With raining heavily, there's heavy snow. Mostly, we still come up with 80. If it's a really good weather, no fog, no snow, no cloudy. Even one of the camera, when I click, you see the camera glass will cover with rain. Those are still mostly you can get.
My suggestion was maybe using spectral imaging that you can see through the haze.
That's what we suggest to the Norwegian Public Road Authority. That could be one option, especially during the night. If there's a lot of snow, if the road is very slippery, if they don't clean it, it will be very dangerous. So if you use hyperspectral or just use the infrared, and that will give, but then you see they need to mount all the camera all over the country, you do all the equipment. That's not something easy decision they are willing to pay for.
Are there any other questions?